So just a review of the big ideas, writing the hypotheses, the null versus the alternative. HO is either mu or P equals the null value. The alternative is that mu or P is either greater than, less than, or not equal to the null value, just depending on the claim that we're trying to test. The P value is the probability of getting results this extreme or more extreme purely by chance, assuming that the null hypothesis is true, and then based on that p-value, if it's a low p-value, then we would have convincing evidence against the null. If it's not a low p-value, then we just don't have convincing evidence against the null. And the way that we decide if the p-value is low is by comparing it to what we call the significance level or the alpha level. So if you have a 10% alpha level, anything less than 10% is considered significant. If you have a 5% alpha level, anything less than 5% is considered significant. Typically, the 5% level is sort of like the standard, kind of like with confidence intervals. A 95% confidence interval is kind of the standard. There certainly are others, but those are kind of the standards and that you'll see most often. Okay, so if you haven't had a chance to do the check for understanding from 9.1a, pause the video. You and your team go do this now. Okay, so the hypotheses for performing the significance test, make sure that you define the parameter of interest. The parameter here is the mean. So mu is equal to the mean amount of calcium in teenagers' diets. The null hypothesis is the status quo, the dull hypothesis. It's that students are getting enough calcium, okay? So mu would be equal to 1,300 milligrams. If you want, you can put the milligram piece in the definition of the parameter of interest, or you can leave it in the hypotheses. It doesn't matter as long as your units of measurement are somewhere in the problem. And then the thing that we're trying to test is, we're not concerned whether or not students are getting teenagers are getting more calcium. We're concerned if they're not getting enough. So not getting enough calcium would be less than 1,300 milligrams. So the null hypothesis, the HO, is mu equals 1,300 milligrams. And then the HA is that mu is less than 1,300 milligrams. Okay, so they do the hypothesis test. They calculate the mean and the standard deviation for a sample, and they get a p-value of 0.1404. So that's a pretty high p-value, no matter what your alpha level is, right? If your alpha level is 5 or 10%, that's still a pretty high p-value. So that's not going to be significant for us. Okay, so in number 2, it says explain what it would mean for the null hypothesis to be true. If the null hypothesis is true, then we think that teenagers do get enough calcium. And that even though we got a value less than that, that just happened by chance. Okay, that just happened to be that this particular sample of 20 teens had less than 1,300 milligrams in their diet, but teens overall are getting enough. Okay, so interpret the p-value. So we have to assume that the HO is true with this p-value. So assuming that the mean is indeed 1,300, the chance that this sample gets a mean less than or equal to 1,198 is 14.04%. Okay, so we always have to interpret the p-value assuming that the HO is true. And so that's a pretty high p-value, and especially if we compare it to a 5% alpha level. So we would not have enough evidence based on this sample to conclude that the mean calcium intake for teenagers is indeed less than 1,300 milligrams. Okay, so even though our sample gave us a number less than 1,300 milligrams, we don't have enough evidence to say that all teens, that overall teens get less than 1,300 milligrams a day. All right, so what we're going to be doing next is working on lesson 9.1b activity. So we talked a little bit about the water crisis in Flint, Michigan yesterday. So today let's consider a situation that would be more maybe applicable to Houston. So this is hypothetical, a local oil refinery improperly disposed of chemicals, PFAS. These are certain types of chemicals which have leaked into the groundwater. The EPS advises a drinking water limit of 70 parts per trillion. Anything under that is considered safe, but anything above 70 parts per trillion of this PFAS is considered dangerous. So officials believe that the water in Houston may be unsafe. So they take a random sample of 200 households in Houston, and they find that the average PFAS level of the sample is 70.5 parts per trillion. Okay, so the sample size is 200. The sample mean is 70.5. And so what we're going to do, what you're going to do in today's activity is work through how to do a hypothesis test with the calculations that we know from last chapter about calculating standard error and things like that. So follow along, work with your group, do the best you can. When you're finished with the activity for today, then come back to this video and watch the debrief, watch the big ideas, and then pause, do the check for understanding, and then check that. Okay? So, state the appropriate hypotheses for performing a significance test using words and symbols. So, we always have to state the parameter of interest. Mu is equal to the mean concentration of PFAS in Houston's water in parts per trillion. So you'll see how I put the units of measurement here in the definition of the parameter. So the HO is that mu is equal to 70. And the alternative, that the research hypothesis, we're trying to decide whether or not it's unsafe to drink the water, which would be greater than 70. So after conducting a significance test, a p-value of 0.045 is found. Interpret this value. So since the p-value of 0.045 is lower than any alpha level that we would generally choose, which is 5% or 10%, we do have evidence that the drinking water has PFAS levels higher than 70 parts per trillion. So based on that p-value, should Houston keep the current water or switch to bottled water? So they should switch, right? The water isn't safe. We have significant evidence against the null hypothesis, and so we're worried, and we have enough evidence to show that there is indeed unsafe levels of drinking water in the tap water. So we should switch to bottled water. Just for a moment here, let's just consider the possible outcomes. So let's suppose that decision to switch to bottled water is wrong. What would be a consequence of that? So if the bottled water is unnecessary and the levels of water, the levels of PFAS in the Houston water supply is actually safe, what would be a consequence of that? So you probably said something like, it's really expensive. It's really expensive to buy bottled water. To make everybody in the city switch to bottled water, there would be a water supply shortage. We can remember what that was like at the very beginning of the pandemic. Oh wait, actually it was a few days before the pandemic. We did have a situation where we had unsafe water, drinking water, and everybody went out to buy bottled water. It was like right before toilet paper became scarce. But yeah, there was not a lot left. Or like when our pipes froze last year, right? There was a real run on water. So that could be a problem in and of itself, right? Just people not having access to clean water. It's very expensive. And then, some environmental concerns. That's a lot of plastic waste for no reason. Imagine if everybody in Houston had to switch to bottled water. And then, just in general, it's a pain in the rear to have to drink bottled water all the time. So that would be a consequence of rejecting the null hypothesis when indeed it's actually true. Okay, so how often will this error occur? This error is going to occur as often as our p-value, right? So 4.5% of the time. So given that we have set an alpha level of 5%, that means that 5% of samples by chance will give us a value as extreme as 70.5. But in reality, the drinking water overall is actually safe. So this is only going to happen about whatever the alpha level is. Now, suppose the p-value was 0.14, kind of like it was in the example from yesterday, or not yesterday, from yesterday's lesson. Should the city keep the current water or switch to bottled water? So a p-value of 0.14, that's pretty high. We probably wouldn't have enough evidence to make the claim that the drinking water is unsafe. But I don't know, I would still feel kind of unsettled. So we would keep the current water, but I would be cautious. I would basically want them to do more research, wouldn't you? So let's just suppose that decision is wrong. So keeping the drinking water when it's actually unsafe. What would be a consequence of that? Well, you probably said that this would be a huge health issue. So here's what we know about PFAS. It leads to higher rates of miscarriage, cancer, brain damage, right? Do we want that happening to people in Houston? So no, we probably don't. So which consequence do you think is more severe, 4 or 7? I think some people might say 7, right? These are immediate health issues. But depending on your point of view, I mean, cost, that can also be a health issue for people. And pollution, that can also later become a health issue. So, but it seems like the near-term issues would be more severe in the event that we chose to keep the drinking water and it was actually unsafe. Okay, so why did we talk about these two possibilities today? So these are type 1 and type 2 errors. So the type 1 error is the error that we described in number 4. It's the null hypothesis is actually true, but we rejected it. And we rejected it because we got a p-value that was low. And the probability of a type 1 error is always equal to whatever your alpha level is. So if you set an alpha level of 5%, 5% of samples that you take will show a value too extreme, but it actually just occurred by chance. Okay, so whatever your alpha level is, that's how often your type 1 error will occur. Your type 2 error, this is the error where the alternative hypothesis is actually true, but we failed to reject the null hypothesis. The calculation of the type 2 error is more complex, and it technically isn't a part of the curriculum for AP statistics. It used to be. I used to teach it, and I don't anymore because it's not on there. So just you need to be able to describe it. You need to be able to identify what it is, and you need to be able to talk about in context what the consequence of that error would be, and to decide whether or not a type 1 or a type 2 error would be more severe. So in terms of your AP statistics requirements for quizzes, tests, and assessments, it's for type 2, it's more about describing what that error is and then talking about the consequence of that. Okay? So I want you to pause the video, and I want you and your team to complete the check for understanding, and then unpause so that you can check your check for understanding. Okay, so you know what? I forgot to show you this little handy little chart. You'll see it in the reading when you do your textbook reading. So This is just a little chart that sometimes we use to help us determine what type 1 and type 2 errors are. So we put on one sort of side of the chart the truth, and then the other is the conclusion that we make. So if the HO is true, but we rejected the HO, we made a type 1 error, and the probability of that type 1 error is equal to alpha. If the HO is true, but we failed to reject the HO, well, we made the correct conclusion, so we're good. If the HA is actually true and we rejected the HO, great, then we made another correct conclusion. But if the HA is true and we failed to reject the HO, we made a type 2 error. The probability of a type 2 error is called beta, so alpha and beta. I don't know, again, I don't think it's in the current AP curriculum to talk about beta, but I just wanted you to know it's an alpha and then a beta. That's why we call it beta. Type 1 and type 2. Okay, so you guys know I'm more of a In-N-Out fan. Maybe you didn't know that, but I'm an In-N-Out fan. Let's put it out there. But this is Texas, and people are very loyal to Whataburger here. So the manager of the Whataburger wants to reduce the proportion of drive-through customers who have to wait longer than 2 minutes to receive their food after placing an order. In my experience, Whataburger takes like 15 minutes even in the drive-through. So yeah, I would really like if they would take less than 2 minutes. So based on store records, the proportion of customers who had to wait longer than 2 minutes was 0.63. Yeah, I agree with that. Okay, so 63% of the time, people had to wait more than 2 minutes for their order. So to reduce this proportion, the manager is going to assign an additional employee to drive-through orders. And during the next month, he's going to collect a random sample of 250 drive-through times. And he finds that the p-hat, the sample proportion of people who took more than 2 minutes to get their order was 0.576. So basically what the manager wants to know is, did this help, right? Did it improve drive-through times? We still didn't get it to be under 2 minutes for everybody, okay? But he wants to know if adding more, an additional employee was helpful, okay? So the null hypothesis is that it didn't help, that it stayed the same, 63%. But the alternative is that it did help. So it reduced the proportion of customers who had to wait more than 2 minutes. And he's choosing an alpha level of 10%. Okay, so the type 1 error would be, according to this chart, that the HO is true, but we rejected the HO. So the type 1 error would be that the HO is true, so adding the additional employee did not reduce the amount of time, but we rejected it. So he thought that adding an additional employee was helpful. Okay. Type 2 error, if I go back over here and look at my chart, type 2 error is that the HA is true, but I failed to reject the HO. So the type 2 error in this setting would be that adding the additional employee did indeed help the proportion go down, but he concluded that there wasn't enough evidence to say that it helped. Okay, so which type of error is more serious? I don't know. It's hard to tell. I mean, type 1, he ends up paying an additional employee to work the drive-through line with no benefits to the company. But the alternative is that people like me continue to wait in the Whataburger drive-through line and get mad, and then we don't come back because we're ticked that it takes so long to get our Whataburger order. So just in my personal opinion, I think for me, the more egregious or the more serious would be a type 2 error, because then you lose customers and that's bad for the company. Now, adding one additional employee per shift, that might also cost the manager a little bit of money. That might be, a detrimental outcome financially for this Whataburger branch. So that could be a serious problem too. I guess it would really depend on how many customers are lost versus how the additional cost per employee. Okay. So based on your answer, Sorry, my daughter came in to ask me a question and I got sidetracked. So based on the answer to number 2, do we agree with the company's choice of an alpha level of 10%? And so this has to do with the type 1 error, right? If the type 1 error is a really serious error, we would want to reduce the probability on that. So we would want to choose a smaller alpha level. But I think an alpha level of 10% is okay because, again, I personally think that it would be better to have a type 1 error than a type 2 error. So let's just say that the manager performs the hypothesis test and they get a p-value of 3%. Okay, that's a low p-value, and so they would reject the null hypothesis in order to say that, yeah, the additional employee probably is helping, so we're going to keep that additional employee on. So interpret the p-value itself. So this is assuming that the HO is true. This is the probability that we got a sample as extreme as we did just by chance alone. So assuming that the true proportion of customers in the drive-through line who get their drive-through orders in in more than 10 minutes, more than 2 minutes is 63%, we would get a value of 57.6%, 3.85% of the time by chance alone. Okay, so by chance alone, we would get a value as extreme as the sample that we collected. Okay, all right, so you've got 9.1 now under your belts. We will talk about 9.2 on Monday and go over in more in depth on how to actually do the calculation for the hypothesis test. But in 9.1, you got a really good sense of, in general, what a hypothesis test does, what its function is, how we use it, how we interpret the numbers that we get, and then what the errors are that we can get. So one other thing that I should mention, and this is in your reading, but again, I'll just mention it, is that there is a bit of a trade-off between a type 1 and a type 2 error. So if you increase the probability of a type 1 error, you will decrease the probability of a type 2 error. And if you decrease the probability of a type 1 error, you will, just by nature, increase the probability of a type 2 error. So alpha and beta are sort of competing values. Okay, so as one goes up, the other goes down. And so deciding what alpha level to choose really should depend on which one is more severe, type 1 or type 2.